In this experiment, you're going to wire the circuit in order to display a binary number on two 7-segment displays. The components that you require are a comparator 74LS85, an adder 7483, a 7-segment driver 7447 and two 7-segment displays. So you have to start by testing each component separately. Let's start with 7485, the comparator. The comparator takes two inputs, A3 to A0 and B3 to B0, compares A with B and indicates if A greater than B on pin 5, if A equal to B on pin 6 and A less than B on pin 7. As usual, you first wire up the power and ground rails. So note that in this experiment we have created a separate power rail on the bottom as well, so that you can easily switch between 1 and 0 as you will be shown later in this video. The next step is to tie the inputs A greater than B, A equal to B and A less than B to 0, 1, 0. This is to ensure that this comparator works correctly. If A greater than B is set to 1, then no comparison will happen. So pin 2 has to be tied to 0, pin 3 to 1 and pin 4 to 0. Next, you find that the inputs are all staggered. So you have B0, A0, B1, A1, A2, B2, and this is a very confusing order. So because of that, you are advised to first wire these onto the breadboard so that you get the inputs to appear as B3 down to B0, A3 down to A0, exactly as shown here. You see that the yellow wire has been used to wire the MSB, the green wire for the LSB. So you are advised to maintain this color coding so that you can easily identify the inputs. In this experiment, input B has been hard coded to 1001. So after you make the connections, you are advised to first check if the inputs are available at the pins correctly. Input B3 is at pin number 1 and you check that that is 5 volts. Similarly, you find that input B2 is on pin number 14 and you again probe pin number 14 in order to ensure that B2 is equal to 0. Similarly, B1 is on pin number 11 and you verify that that is 0 as well. Finally, you ensure that B0 on pin number 9 reads a value of 5 volts. On input A, you can feed some test value, and in this example we have picked 1100, which is 12, and we know that it is greater than 9, and hence we expect that the output OA greater than B should be equal to logic 1 or 5 volts. So you probe pin number 5 and make sure that that reads 5 volts. Similarly, you can probe pin number 6 and 7 to ensure that OA equal to B and OA less than B are both 0 volts. Next, we switch the input A3 from VCC to ground. So the input now becomes 01004, which is less than 9. What we did here was to simply switch the yellow wire from the VCC rail on the left to the ground rail on the right. This is the advantage of having both rails nearby. So now again we probe using the voltmeter to see that the pin 5, which is OA greater than B, is 0. Pin 6, which is A equal to B, is also 0. And finally, we probe pin 7 to ensure that the output OA less than B is 5 volts or a logic high. Thus, we are sure that the comparator is fully functional now. Next, we verify that the adder 74LS83 is functional. The adder takes two 4-bit numbers A4 to A1 and B4 to B1 and gives you a sum output of sigma 4 to sigma 1 and a carry out of C4. C0 is the input carry that needs to be grounded. In this experiment, we either add 6 or add 0 to the binary number that is given, and hence you can go ahead and test this adder with the input A hard coded to 6, which is 0, 1, 1, 0. Important to note that unlike the other 7-4 series, BCC is on pin number 5 and ground is on pin number 12. Inputs A4 to A1 have to be connected to 0, 1, 1, 0 respectively, and C0, which is pin number 13, needs to be grounded in this experiment. So you can now give some random inputs to the inputs B4 to B1 and verify that the sum and carry are appropriate using a voltmeter like we did in the comparator. Next, we would like to test the BCD to 7 segment driver and also the 7 segment display. 74LS47 is the BCD to 7 segment driver. If you provide a binary input DCBA, with D being the MSB and A being the LSB as shown here in this pin diagram, then the outputs small a to small g will be appropriately selected so that the right LEDs will glow and display the digit appropriately. The output small a to small g from the previous pin diagram have to be fed to this pin diagram as shown here. This 7 segment display is a common anode display, and therefore the common node 3 or 8 needs to be connected to VCC. You also need to ensure that a current limiting resistor of about 300 ohms is connected between pins A to G and also the decimal point DP and the inputs to the 7 segment display. This is how the circuit should look after you have wired the driver to drive the 7 segment display. So you see that the inputs have been connected to all zeros and hence the display is showing 0. Now if you switch, let's say the MSB, which is the input D, which is on pin number 6, from 0 to VCC, you will find that the output will go from 0 to 8. Now we have connected the inputs to 1001, which means that the display will show 9. However, if you connect the lamp test bar signal on pin 3 to ground instead of VCC, you will find that all the LEDs start glowing on the display. So this is just a way of testing that the display is functional even before you start your experiment. So all you have to do is connect lamp test bar on pin 3 to ground instead of VCC. Now this is the final output that you are expected to show. So what is shown here are two displays. On the left is the MSB of your decimal display and on the right is your LSB of the decimal display. The input is 1100 that has been given to the comparator, and therefore you see an output of 12. If you now switch the MSB of the input to the comparator from 1 to 0, that is, you make the input to the comparator 0, 1, 0, 0, the output should now switch to 0, 4. And that is exactly what you observe here.